Hello everybody, my name is Iman. Welcome back to my YouTube channel. Today we're going to be continuing our lecture on chapter 4. Previously we talked about net ionic equations, and today what we want to do is build our knowledge of this by extending into acid-base reactions. The first thing we want to do is define a neutralization reaction. A neutralization reaction in aqueous solution is a reaction between an acid and a base to form salt plus water. We're going to see a few examples of this by starting off first with a neutralization reaction of a strong acid with a strong base. So we're going to consider the reaction of hydrochloric acid, which we know is a strong acid, with sodium hydroxide, which we know is a strong base. So we're going to go ahead and write those as our reactants, hydrochloric acid plus sodium hydroxide. What are the products? The products are going to be salt plus water. And you can see this if you swap ionic partners. So this H is now going to be paired up with this hydroxide ion. That's going to give us water. And now the sodium is going to be paired with the chloride to give us sodium chloride, which we know is a salt. So this reaction right here, this is the molecular or formula equation. Now we can begin to get closer to the net ionic equation by first writing the total ionic equation. Here, all strong electrolytes are going to be written as separated ions. So hydrochloric acid, this is a strong electrolyte. So now we write it as its components, H plus and Cl minus. Sodium hydroxide is also a strong electrolyte. We write it in its separate ions, sodium plus hydroxide. Sodium chloride, the salt, is also a strong electrolyte. So we write it as separated ions, sodium plus chloride. Water is not a strong electrolyte here. We write it as H2O. It's a liquid. It will stay as such. Now what we can do is get rid of our spectator ions. So anything that appears on both the reactant and the product side gets eliminated. So sodium is both on the reactant and product side. Same with chloride. Now what we have left are the ions that actually participate in the reaction. What we have is H plus OH minus hydrogen ions plus hydroxides gives us water for the product. This is the reaction that's happening. And so the conclusion is, since strong acids and strong bases are strong electrolytes that completely dissociate into ions, the only ions that are not spectator ions are the H plus and OH minus to yield water. All right, so whenever you have a strong acid, strong base reaction, your net ionic equation is going to look something like this. Now let's do another example. What about the net ionic equation for a weak acid, strong base? So let's consider the reaction of acetic acid. So that is a weak acid. This is going to look like HC2, H3O2 with sodium hydroxide. Sodium hydroxide is a strong base. Let's go ahead and write the molecular equation. This is acetic acid plus sodium hydroxide. Let's have a swap of ionic partners. This H is going to be paired with the OH to give us water. Perfect. Remember, a neutralization reaction does yield water, and it also yields a salt. The salt is going to be, the sodium is now going to be paired with acetate to give us sodium acetate. That is our salt. Now we want to write the total ionic equation. Here, remember, strong electrolytes are written as separated ions. All right, and a weak acid or weak electrolytes, this is not going to be written as ions. So if we're looking at our reaction, this acetic acid is not going to be written as separated ions because it's a weak electrolyte. Sodium hydroxide, however, will be written as separated ions. We write sodium plus and hydroxide. Okay, as for the product, the salt is a strong electrolyte, so we write it as its component, sodium and acetate. And then, of course, we have water written as water. Now, here in this total ionic equation, we're going to get rid of any spectator ions. We only have one spectator ion. Sodium appears in both the reactants and the products, so we're going to go ahead and get rid of that. Now we can go ahead and write our net ionic equation. We have acetic acid plus hydroxide ions gives us acetate and water. Here the conclusion is, since a weak electrolyte forms very few ions when dissolved in water, any weak acid should be written in its neutral molecular form in the total ionic and the net ionic equations. So keep that in mind when you're working with, for example, a reaction of weak acid with a strong base. Now, what we want to do is tackle an example problem together. This problem says, write the net ionic equation for the reaction that occurs when an aqueous solution of sodium sulfate is mixed with an aqueous solution of lead 2 nitrate. All right, nitrate. Let's go ahead and do the first step. The first step is obviously to write the molecular formula, which is the molecular equation, which is the total reaction written out. Okay, what we have is sodium sulfate. We'll write that out. Sodium sulfate. Now, sodium has a plus charge. Sulfate has a 2 minus charge. We swap those charges, and what we get for sodium sulfate is Na2SO4. The other thing we're dealing with in our reactants is lead 2 nitrate. Lead is Pb. It has a 2 plus charge. And then nitrate is just NO3 minus. Again, we're going to swap charges here. Lead 2 nitrate looks like Pb, NO3 2. And so for our reactants, we have Na2SO4 aqueous plus lead 2 nitrate. Aqueous. All right, what does our reactants look like? Well, what we're going to do here is we're going to start by swapping ionic partners, of course, making sure that the ionic formulas are overall neutral. And then what we want to do is balance the equation. Okay, so when we swap ionic partners, the sodium from sodium sulfate is going to be combined with nitrate. So now we're going to have sodium nitrate. And then we're also going to have, and this is going to be aqueous. Let's write aqueous. And then what we're going to have is lead that partners up with sulfate. So this is going to be PbSO4. This is going to be a solid. All right. Now, we want to balance the equation. The only thing that we need to do to balance the equation is simply put a 2 right here. So what I'm going to do is go ahead and rewrite this to look a little bit better for us so that we can move into our next step. And also we can talk about how we knew what was a solid in this equation. So let's go ahead and write this out. NO3 aqueous plus PbSO4 sulfate. Now, when we apply the solubility rules, NaNO3, sodium nitrate, is soluble based off of the solubility rules we talked about earlier, and PbSO4 is insoluble. Remember, sulfate is soluble except when it is paired with a couple of different cations. Lead 2 is one of those examples. And so actually lead sulfate is insoluble. It forms a solid. Now, we also added a coefficient of 2 here to balance this out. We've talked about balancing equations before, so we won't spend too much time here, but you can go ahead and check for yourself. The next step, now that we have the molecular equation written, let's go ahead and start to write the total ionic equation. Total ionic equation. So how do we approach this? Again, we're going to look at every reactant and every product, and we're going to ask, is it a strong electrolyte? Every strong electrolyte should be written as dissociated ions, since that is how it exists in aqueous solution. Remember that strong electrolytes are 1, strong acids, 2, strong bases, and 3, soluble salts. Sodium sulfate, lead nitrate, and sodium nitrate are all strong electrolytes since they're soluble salts. All right. The only one that is an insoluble salt is lead sulfate. So we're going to write everything else as separated ions. All right, so we have 2 sodium plus aqueous plus SO4 2 minus aqueous plus lead 2 plus aqueous plus 2 NO3 aqueous. These are all in their separated ions for the reactants. Then for the products, again, we have 2 Na plus aqueous from the sodium nitrate plus 2 NO3 minus aqueous. And then, of course, lead sulfate is insoluble, so we write it as such. Now we want to eliminate anything that appears in both the reactants and the products. In the reactants, we have 2 sodiums, and in the products, we have 2 sodium ions. So we're going to eliminate that. That is a spectator ion. Same goes with nitrate. 2 of them appear in the reactants and 2 of them appear in the products. So those are also spectator ions. What we're left with is what is going to be written for our net ionic equation. We have sulfate lead in the reactants and lead sulfate in the products. So now we can go ahead and write our net ionic equation. All right. We're going to write the net ionic equation by removing the spectator ions. Those are what appear on both sides of the arrow, completely unchanged. What we get for our net ionic equation is lead 2 plus aqueous plus sulfate minus 2 minus aqueous gives us lead sulfate solid. That is our net ionic equation. All right. So the takeaway message is, remember these points. 1, only strong electrolytes are written as ions. That means that you only separate strong acids, strong bases, and soluble salts. 2, all weak electrolytes, insoluble salts, and non-electrolytes are always written in their neutral form. Do not write weak acids and weak bases as separated ions. And then 3, be sure that all spectator ions are removed. So we just did a good example for how to write net ionic equations. With that, we can go ahead and move into our 8th objective. The 8th objective is titled Stoichiometry of Precipitation Reactions. Here we want to combine our understanding of solutions with stoichiometry. Previously, we've covered the principles of chemical stoichiometry. This is the procedures for calculating quantities of reactants and products involved in a chemical reaction. Recall that in performing these calculations, we first convert all quantities to moles and then use the coefficients of the balanced equation to assemble the appropriate mole ratios. In cases where reactants are mixed, we have to first determine which reagent is limiting, because the reactant that is consumed first is going to limit the amount of products formed. These same principles apply to reactions that take place in solution. However, there are 2 points about solution reactions that do need emphasis. The first is that sometimes it is difficult to tell immediately what reaction will occur when 2 solutions are mixed. Usually we do some thinking about the various possibilities and then decide what probably will happen. The first step in this process should always be to write down the species that are actually present in the solution. So like writing a net ionic equation. The second special point about solution reactions is that to obtain the moles of reactants, we must use the volume of the solution and its molarity to get to that point. So with that out of the way, the best way to really understand what this encapsulates is by doing some problems together. So we're going to start with this first problem that is going to sound really familiar to the example problem that we just wrote the net ionic equation for. So let's read it. This problem says, when aqueous solutions of sodium sulfate and lead nitrate are mixed, lead sulfate precipitates. Calculate the mass of lead sulfate formed when 1.25 liters of 0.0 0.05 molarity lead nitrate and 2 liters of 0.025 molarity sodium sulfate are mixed. Okay, let's get this in order. First thing, we're going to identify the species present in the combined solution and determine what reaction is actually happening. All right? When the aqueous solution of sodium sulfate and lead nitrate are mixed, the resulting solution is going to contain the ions sodium, sulfate, lead, and nitrate. And since sodium nitrate is soluble, but lead sulfate is insoluble, the product is going to be solid lead sulfate. That is what's going to form. All right. So thinking about it like that, the best thing to follow up is to write your molecular equation. Then write your total ionic equation, and then try to figure out finally the net ionic equation. All right. Now, thankfully, we just did that in a previous problem. So we know what the net ionic equation is. So the second step is to write that balanced net ionic equation, since we thought through what species are present, what dissociates, what cancels out in the reactants, what gives us finally our balanced net ionic equation. It's just going to be lead 2 plus, just like we saw previously, aqueous, plus sulfate 2 minus aqueous. That gives us solid lead sulfate. So had we not done this previous example where we worked exactly through this reaction, you would have to go through these steps so that you're able to obtain the net ionic equation, because we're going to need it for the steps that follow. The step that follows is that we're going to calculate the moles of reactants so that we are able to identify the limiting reagent or reactant. So let's do that. Let's calculate the moles of reactants. All right. We're going to start off with lead. We're going to figure out first the moles of lead. Here's the information that we're given. We're given that we have 0.05 molarity of lead nitrate. And so what that means for us, considering our net ionic equation just contains lead ions, it means that we have 0.05 molarity of lead ions. And that makes it useful for us to calculate the moles of lead ions in the volume, because what we can do is we can write the volume we have of lead ions, all right, and use the molarity of lead ions. I know we're given it in the form of lead nitrate, but remember, we told ourselves, because we worked through the net ionic equation, that we only really have lead in participating in the reaction here. So what we really have is 1.25 liters of lead, and the molarity is 0.05 for lead ions. So we write 1.25 liters. All right, we multiply this by the concentration, the molarity, which is 0.05 molarity, which is moles of lead ions per 1 liter. Liters cancel out. We're going to get our final answer in moles of lead. So we just unlocked something here in stoichiometry. We can use molarity to get rid of units sometimes. And we just did that because all we have is a volume of lead ions and a molarity of lead ions. And we can use those two things to get the moles of lead. Here, if you plug this into a calculator, you get 0.0625 moles of lead. All right. Now let's do the same thing with sulfate. Now we're given that we have 2 liters and 0.025 molarity of sodium sulfate. But again, we know that this can be extended just to the sulfate ions. So what we have is 2 liters of sulfate ions at a concentration of 0.025 moles of sulfate per liter. So we're going to do the same thing to figure out the moles of sulfate. So we set this up, all right, and notice how liters cancel out. We're going to get our answer in moles of sulfate. Beautiful. If you plug this into a calculator, what we're going to get is 0.05 moles of sulfate. So now we have moles of lead and moles of sulfate. The next thing now that we have that is to determine which reactant is limiting. Now we can do this the long way, all right? Or we can do it the easy way. And actually considering the information we have, we can actually do it the easy way. Let's look at our reaction. All right, what is our reaction? We have 1 mole of lead and of lead 2+ and 1 mole of sulfate that gives rise to 1 mole of lead sulfate. Okay, because lead and sulfate react in a 1-to-1 ratio, the amount of sulfate is going to be the limiting reagent because we have less moles of it. Because there's this 1-to-1 ratio, whichever species has less moles is going to be our limiting reagent. That is going to be sulfate with 0.05 moles. Now that we know that, we can begin to calculate the moles of product. All right? We can calculate the moles of product. Now we know that sulfate is the limiting reagent, and that means that the lead ions are present in excess. All right? They're going to be present in excess. I'm sorry, not access. I can't believe I said that. The lead ions are present in excess. So that means this 0.05 moles of sulfate is going to be what we're going to use to calculate the moles of lead. Now, I'm going to tell you, just using logic, how we can figure this out, and then I'll do the stoichiometry for you just to make sure that we're all on the same page. If the lead ions are present in excess, that means our limiting reagent is sulfate. If we use the moles of sulfate, we can figure out the moles of product. It's going to be a 1-to-1 ratio because there's 1 mole of sulfate to 1 mole of lead sulfate, which means, using that logic, we're going to have 0.05 moles of solid lead sulfate. But we can also just do this in stoichiometry. If we have 0.05 moles of sulfate, all right, we can do a mole-to-mole ratio between the sulfate and the product, like we've seen before in previous chapters. For 1 mole of sulfate, we have 1 mole of lead sulfate, all right? 1 mole of lead sulfate, 4. And now we can figure out what our moles of lead sulfate is because these cancel out, and look at that. We have 0.05 moles of lead sulfate that will form. So that's what I mean when there's this 1-to-1 ratio. It becomes really easy to kind of just look at things and decide. But if that's not easy for you yet, which is pretty normal considering this is general chemistry and we're only on chapter 4, so we're still building our chemical intuition, you can go ahead and just rely on your stoichiometry knowledge and write things out in a step-by-step fashion. All right, that's how we were able to figure out also that just looking at the moles of lead 2+ and moles of sulfate, why it was so easy for us to determine which one was limiting. All right, so now we know. Now we know the moles of product, 0.05 moles of solid lead sulfate. Now we can do our last and final step where we can convert to grams of product, all right? Because the problem asks us to calculate the mass, so we need grams. So all we have to do now, and ignore that I'm using this space for the second problem, we have 0.05 moles of lead sulfate. All right, we can use the molar mass of lead sulfate to get the grams. You can do this really easily by just summing up the mass of lead that you can get from the periodic table of sulfate and of 4 oxygens. I'm just going to give you what that is, 303.3 grams of lead sulfate per 1 mole. And if we plug this into a calculator, we're going to get 15.2 grams of lead sulfate. And that is our final answer for this problem. Now for the second problem, I'm going to circle it here because we kind of wrote over it. I want you to attempt this problem. Here in the next second, I'm going to have a 1-second pause. I'm going to tell you what the answer is. I want you to try to work through it first before you hear the answer and double check your work. Feel free to ask me questions down in the comments below if you are having trouble reaching the answer. But the answer for this problem, the mass of sodium chloride that you're trying to calculate, is going to be 8.77 grams of sodium chloride. Try to work through the steps and see if you can get that answer. Other than that, we can move on to our last and final objective, which is titled acid-base titrations. Again, we can talk about solution stoichiometry beyond just precipitation reactions. So here, we're going to focus on acid-base reactions, acid-base titrations to be specific. Now, we know that stoichiometry is based on the relative number of moles of reactants and products. In acid-base titrations, a solution of an acid is added to a solution of a base until that neutralization reaction is complete. And so you have a certain amount of unknown solution in a Erlenmeyer flask. And since we're analyzing the unknown in order to determine its concentration, the unknown is called the analyte or the titrant. Now, the titrant is a solution of known concentration that's placed in a burette, and it's going to precisely measure the volume of liquid that we will deliver here to the analyte. The titrant is slowly added from this burette until the equivalence point is reached. What is the equivalence point? This is the point in the titration where the number of moles of H plus from the acid is going to be equal to the number of moles of OH minus or hydroxide from the base. The equivalence point is also noted by a change in color of the solution in that Erlenmeyer flask. This change of color occurs because a small amount of an indicator is usually added to the analyte. An indicator is just a dye that changes color depending on how acidic or basic a solution is. Now, to solve a simple titration problem, what you're going to have to do is write the balanced acid-base neutralization reaction, and then you can use molarity and volume to determine the number of moles of acid and base. Now, this kind of topic, titrations, this is a very brief introduction. It's going to have its own chapter later down the line. But really, our main takeaway is to be able to do problems relating to titrations, but really the focus here is everything we've covered up to this point, being able to extend stoichiometry to solution-based problems. So let's read this problem together and tackle it together. What volume of 0.277 molarity nitric acid is required to completely neutralize 24.7 milliliters of 0.192 molar barium hydroxide? Okay, so always begin every stoichiometry problem by writing the balanced equation. So for the sake of time and also because we've done a lot of balancing equation problems, I'm going to go ahead and write this down for us. All right, what we have is 2HNO3 nitric acid. All right, this is aqueous, plus barium hydroxide, aqueous. What does this give us? All right, remember, this is acid-base. It's going to give us a salt and water. And you can just think of this as kind of like swapping ionic partners. So we have barium nitrate plus, and that is aqueous, plus water, H2O liquid. Okay, so now that we have this, let's also start to think about the information we were given in the problem, because they gave us some good information. They told us the molarity of the acid, it's 0.277 molar, and they also did give us the molarity of barium hydroxide as well as the volume. So they said 0.192 molar, and we have 24.7 milliliters, all right? We're trying to use this nitric acid with this specific molarity, all right? This is going to be used to neutralize the 24.7 milliliters that we have of barium hydroxide at a 0.192 molarity. What are we trying to figure out then? Essentially, we are trying to figure out the milliliters of nitric acid we're going to need. So here's what we can do. We can use 3 steps for dimensional analysis that we've actually used in previous chapters. First one, we're going to write down what we want to know. Second, we're going to start with the given measured quantity. And 3, we're just going to apply conversion factors to cancel unwanted units. So what are we trying to figure out? We want volume of nitric acid. So number of liters or milliliters, whatever, of HNO3 solution. Okay, what are we given to start? We're given 24.7 milliliters of barium hydroxide. Let's quickly just convert that to liters and we'll start from there so we can get our answer in liters. Okay, so this is just going to be 0.0247 milliliters. That's what we're starting off with. What we can do now, and here's what's interesting and what we saw in previous problems with the precipitation solution, is we can use molarity to get rid of certain units and use it in our conversion factors here. And so we have this milliliters. We can use the molarity of barium oxide because this is the liters of barium hydroxide. We can use its molarity to get rid of the units here. All right. And I accidentally wrote milliliters here. This is supposed to be liters. We just converted it so we can use our conversion factor for molarity to get the liters canceled. So what is our molarity? 0.192. That means we have 0.192 moles of barium hydroxide per milliliter. Liters cancel out. Now, what we can do, because again, our goal is to get liters of nitric acid, let's do a mole to mole conversion. All right. What is our mole to mole conversion? We have 2 nitric acids to 1 barium hydroxide. So what we can write is 1 mole barium hydroxide to 2 moles nitric acid. Wonderful. Now, moles of barium hydroxide canceled. Last conversion, we can convert from moles to liters. How? We're going to use the concentration of nitric acid to do that because the units for molarity is moles per liter. So what we can do now is we can write, what is our molarity for nitric acid? 0.277. So we can write 0.277 moles of nitric acid. We're writing it in the denominator so that moles of nitric acid can cancel out per 1 liter. Now we can get our answer in units of liter for our nitric acid solution. Plug this into a calculator. What do we get? 0.0342 liters. And we can convert this to milliliters if we want. It's just going to be equal to 34.2 milliliters of nitric acid is required to completely neutralize 24.7 milliliters of a 0.192 molar barium hydroxide solution. All right. And with that, guys, we've completed everything for this chapter. I really hope this was helpful. Let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.